Good evening and welcome. I am Ron Fricker, Interim Dean of the Virginia Tech College of Science. I am delighted to welcome you to the J. Mark Sowers Distinguished Lecture Series in the College of Science. We are very pleased to have you join us today for this special talk by Dr. James Gates. The J. Mark Sowers Distinguished Lecture Series was initiated in February of 2017 with the goals of exchanging new and innovative ideas in science and providing opportunities for the university community and general public to interact with eminent scholars. Thanks to the generosity of Mark and Debbie Sowers, sponsors of today's event and this lecture series, we are able to do that not only within our college, but also to offer those ideals and inspirations to our larger community. Today's event is unique as it is only the third time this distinguished lecture has been held entirely virtual. And while we enjoy opportunities to gather in person, this webinar format has allowed us to expand our audience to alumni and friends across the Commonwealth and around the globe. On behalf of the university, I would like to thank Mark and Debbie Sowers for their tremendous support in creating this lecture series. Their passion for science and discovery has made it possible for us to bring 14 distinguished scholars and exceptional speakers to Virginia Tech in recent years. Tonight, we have a special guest joining us to introduce Professor Gates. Earlier this year, Virginia Tech named Dr. Kevin Pitts the next dean of the Virginia Tech College of Science. Dr. Pitts is currently the Chief Research Officer at Fermi National Accelerator Laboratory and a Professor of Physics at the University of Illinois at Urbana-Champaign. While he will officially step into his new role on June 13, he enthusiastically agreed to join us this evening to introduce our distinguished speaker. Kevin, we are delighted to have you joining us today for this special event, and I now ask that you please introduce Dr. Gates.
Thanks very much, Ron. Good evening, everyone. I'm really excited to be joining the Virginia Tech family, and I look forward to getting started in Blacksburg very soon. I'm also delighted to be able to participate tonight in this special event. I want to add my thanks to Mark and Debbie Sowers for their generosity that makes this event possible. Thanks also to Mark Pitt, George Minnick, and the physics department for their work in putting this together. It is my pleasure to introduce Professor James Gates. Jim is the Ford Foundation Professor of Physics at Brown University, where he serves as the director of the Brown Theoretical Physics Center and as a faculty fellow in the Watson Institute for International Studies and Public Affairs. He is a theoretical physicist who is well known for his work on supersymmetry, supergravity, and superstring theory. He received 2 BS degrees and a PhD from the Massachusetts Institute of Technology, where his doctoral thesis was the first on the topic of supersymmetry. In 1984, he co-authored Superspace, the first comprehensive book on supersymmetry. He followed his PhD with postdoctoral positions at Harvard and the California Institute of Technology, and he then began a 34-year career as a faculty member at the University of Maryland, where he was the John S. Toll Professor of Physics. He moved to Brown University in 2017. Professor Gates has received numerous honors for his scientific work, including fellowship in the American Physical Society, the American Association for the Advancement of Science, and in 2013, he was elected to the National Academy of Sciences, becoming the first African-American theoretical physicist so recognized in its 150-year history. That same year, President Obama awarded him the National Medal of Science at a White House ceremony. Professor Gates has also been active in science policy and the public policy arenas, serving on the U.S. President's Council of Advisors on Science and Technology, on the Maryland State Board of Education, and the National Commission on Forensic Science. He served also as president of our professional society, the American Physical Society, during this challenging past year of 2021. And in my current position as Chief Research Officer at Fermilab, I am proud to tell you that we recently announced the James Gates Fellowship in Theoretical Physics at Fermilab that prioritizes the inclusion of first-generation college graduates and the representation of historically and contemporarily minoritized individuals underrepresented in theoretical physics. With that, I welcome Professor James Gates. Jim, thank you for all of your contributions, and thank you so much for joining us tonight. The floor is all yours.
Well, Kevin, thank you for that generous introduction, and thank you for the brevity. I often have people try to give a description of all that I do because I have essentially 4 simultaneous careers. And unfortunately, if you try to do that, it burns up a lot of time. On one occasion, a friend of mine was sitting next to me as this was occurring, and he leaned over and said, "Jim, you know, that is what we say is about a person, an introduction, a person that needs no introduction. And then he leaned over and said, but that's an introduction that needs no person. So why don't you get up there and get started? So I've always appreciated that comment. So let's get started tonight. So the title, but before we start, I would truly be remiss unless I thank the Sowers family for their support of this. I had a great time with Dr. Sowers earlier today, and hopefully we'll get a chance to speak together again sometimes, and maybe even a visit to your campus, because I have been on your campus on at least 3 or 4 different previous occasions. So let's get started now.
Something big has been erupting all around us. Recognized by those that understand that they too are big, but to shape the universe that in turn shapes them, they must align with the best. The network that is made to help them be the best. This is not just about speed and reliability. It's about being part of a movement that involves you.
So folks, the title talks about and beyond, because I have had a strange life. And I've actually done 2 commercials. You just watched the first 2014 commercial, which I did for Verizon. And of course, what in the world is a theoretical physicist doing television commercials? Well, let's see how we got there a little bit. I'm gonna start with mom and dad. This is a picture of my father in 1962, a picture of my mother in 1942. My father served 27 years in the US Army. And as a consequence, although I was born in Florida, so I am a native Southerner. I know I don't sound like one because almost immediately we started moving. And by the time I was in 6th grade, I had been in 6 different schools. Before I began school, we lived in Canada, where my mother took me to see this. This is a picture of the place where we live, St. John's, Newfoundland. And she took me one day to see a movie at 4 years old. And this movie fired my imagination. At 4 years old, what I really got from it was, I understood these things called rockets exist. But more importantly, I heard this word science. And from my 4-year-old mind, science was a doorway to adventure and fun. And what else would a 4-year-old child wish to have in their life, especially a little boy? So supposedly the next part, I came home and I was told, and I tried to explain to my father how rockets work. Well, we can imagine how comical that would have been if there had been smartphones back then, but that's what Dad said happened. And this movie, which I'm showing you the movie bill for, is in fact the source of my inspiration to do science. As you can see, it starred Eva Bartok and Howard Duff. And one of the things that to me was always very interesting as I reflected on my life was, why did Mom take me to see this movie? Because you see, my mother was a typical 1950s housewife. She didn't even know how to drive a car, but she knew how to take care of her 4 children and be a good spouse to my father as his military career advanced. Unfortunately, she died when I was 11, but she left behind this legacy where I heard about space. This is me in 2nd grade. At this point, I was trying to learn to read, and I had great difficulty learning to read. However, arithmetic was very natural for me. And that's sort of a reflection perhaps of my family history, because my grandfather could neither read nor write, but he could do some simple arithmetic. My dad never finished high school, but I remember as a child watching him study trigonometry and some beginning calculus as he was earning his general equivalency degree, the GED, in place of his high school. And so we liked math in my family for at least 4 generations. I had children that looked like they're going to be physicists, and you're going to meet them later. As I was struggling to read, my teacher informed my parents that if they brought home some books about something I enjoyed, I'd probably learn to read very quickly. And so my father brought home these 4 books whose covers you see, all by an author named Willie May, who actually wrote children's books about space travel. This is like 56 and 1957. And he actually also appears in a Disney film called Man in Space. And so if you want to actually see the guy who wrote these books, that video is actually at YouTube. So I was reading very quickly. Oftentimes these days when I send emails messages, at the bottom it says, please overlook all errors of spelling, punctuation, and grammar. My first language is mathematics, and my second language is actually English. And it's recognition that that's almost literally true as I began to start school. I also started reading science fiction at that point in time. These two books were written by an author whose name you see written on the covers as Paul Finch. Paul Finch was a pseudonym for Isaac Asimov. So I was in love with Isaac Asimov science fiction stories and science fiction in general for most of my young life. At 14, my real dream sort of began. I learned about this place called MIT, the Massachusetts Institute of Technology, but no one in my family had ever gone to college. So although I didn't know at the time I was dreaming about it, it was highly unlikely that a person of the African diaspora would wind up having the opportunity to go to MIT, because largely people of color and diversity did not exist on that campus. But I was very fortunate. I applied to college in 1969. That was the first year that major institutions decided that people who look like me could attend their colleges. And it's more complicated than that, because actually the first African-American student to attend MIT did so in the 1890s, but there were never more than a handful of students. Whereas in 1969, MIT decided to see what would happen if we let more than a handful attend. When I was 14, however, and these dreams were starting, I was still in comic books. In particular, I'm showing you my favorite comic book characters, the Fantastic Four. I had many hours of reading their adventures, created by Stan Lee as the author and Jack Kirby as the artist. And this is a cover from the first Fantastic Four issue in which the character of the Black Panther appeared. They were actually quite advanced. If you look back at the literature, they wrote essentially on diversity, they wrote on discrimination, and it was all wrapped up in these stories about superheroes. This is a particular cover where the Fantastic Four and the Black Panther on the left side of the screen, but the Inhumans, who were mutants, or actually sort of a slightly different species from humans, and were such that they had to live in hiding so that humans wouldn't actually come after them. And there's a theme of characters called X-Men, where you see Stan Lee pressing on the issue, why can we not be accepting of all of us who participate in this human adventure? He also wrote this story about the hate monger, a character whose superpower was to have a ray gun that he could turn on people and cause them to hate each other. And so, it turns out this character is a very famous historical figure. And if you want to know who it is, you'll have to read it, because I don't want to give away the surprise. In 1969, I graduated from Jones High School in Orlando, Florida. Now, I was born in Florida, in Tampa. And up until 6th grade, I had gone to 6 different schools, mostly in Texas, in El Paso, Texas, and San Antonio. But in '63, my father remarried after my death a year earlier of my biological mother. My stepmom was a teacher in the Orlando public school area. And so I attended Jones High, which was historically the only place that African-American students were allowed to get a secondary education in Orlando. I had fantastic teachers in this high school. I'm showing you some of them. Miss Leslie Weaver and Miss Thelma Dudley were my English teachers. And as you can probably hear from the way I speak, they were true taskmasters and having their students learn to speak the King's English. Miss Edna Williams was my geometry teacher. She's the first person who made clear to me what was the meaning of the term mathematical logic, because her geometric proofs had to be exactly precise and correct. Mr. William Saunders was my Algebra 2 teacher, so I started learning at least the foundation for calculus under his tutelage. Mr. Reuben Patrick was my French teacher. And then finally, the teacher who had the most impact on my life was Mr. Freeman Coney, who you can see in the bottom right-hand corner. Mr. Freeman Coney taught physics. And when I was a junior in high school, I took a physics class, basically because I was sort of running out of classes. I had taken the standard courses and had sort of advanced through them at an accelerated rate. Normally, juniors didn't get a chance to take physics, but since I didn't have anything else to take, I was allowed to take Mr. Coney's class. I was the only 11th grader in the class. And one day, Mr. Coney saw one of his students with a comic book trying to hide the comic book in a textbook and pretending to be reading the textbook. So Mr. Coney tried to draw the student out by asking the student a question. The student answered the question without looking up. Mr. Coney then tried a more difficult question and got the same result. And then finally he got a question that he figured no student in the class would be able to answer, and he asked it, and he got the same result. At that point, he said, he realized that student might actually become a physicist. Now, I don't actually remember all this happening, but Mr. Conley told this story many times in my life. And of course, I was that student. This is me as a senior. And so I'm still reading a lot of comic books as a senior in high school, something that most of my high school classmates had stopped doing, but something which had an incredibly important impact on my life. Because you see, in order to do theoretical physics, you actually have to have an active imagination. In fact, Albert Einstein once said, imagination is more important than knowledge. When I was very young, I couldn't figure out why he said that, because to me, knowledge was how you got to the moon with science and technology, whereas imagination was the world of Marvel comics and science fiction television programs, like The Twilight Zone, The Outer Limits, science fiction theaters, which were all favorites of mine, Rocky Jones' Space Ranger as I was growing up. And so why was imagination more important? We'll come back to that near the end. But my dream came true. 1969 was the year when people who looked like me had a fair shot at getting into MIT. And to my very great surprise, I got in. I have to tell you that I almost didn't apply. You see, in our society, African-American young people are often told that we are intellectually deficit, that we don't have the capacity to do this. And although while I was in elementary school, living on Army posts, I was in a diverse environment. I had students, friends who were Hispanic American, Asian American, European American. We were all just kids together. And so I had actually always been one of the best students in the class. That was my lived experience. But when we moved to Orlando, things changed when I was 11, 12 years old. And one day, I'll never forget meeting an African-American student in my 6th grade class. His name was Michael. I can't remember his last name. But Michael made an astounding statement. He says, you know, you seem pretty smart. But using his words, he said, but you can never be as smart as a white boy. And I was stunned by that because, you see, I had come from classes where it was evident that I was smarter than a lot of other kids of other ethnicities. But by the time I had graduated, was graduating from 12th grade, those lessons were dim in my memory. And I had started to internalize the fact that maybe I didn't have it to make it to a place like MIT. Now, I told you at 14, I first heard about this place. And I told my father that night that I finally had an answer to the question he had asked since I was in 1st grade, which was, what college are you going to go to? And that evening I said MIT. And so coming up to my senior year, I took the SATs and the achievement test, and I did really well in physics and pretty good on the SATs. As a consequence, I started getting letters from universities inviting me to apply. And one of those letters came from MIT. So I would show them to my father and then put them away. And a few weeks later, Dad asked me, he said, well, did you apply to MIT? And I said, no, Dad. And he said, isn't that the place that you were talking about going to when you were 14? And I said, sure, that's the place. But I also said, Dad, you know they don't let people who look like us go to those kinds of places. And my father, who spent 27 years in the US Army, said, son, you're going to apply. And believe me, as a sergeant major, he was used to getting his way, so I applied. I didn't think I was going to get in. But a couple of months later, I came home and he was on the front porch. I tell people up north that you don't know what rocking couches are, but we sure know what they are in the South. And he was in our porch rocking couch. And it was unusual because you see, my dad was never home before I got home from school. But he was home this one particular day. And I walked up and I wondered what was up. And as he caught sight of me, he smiled the biggest smile I had ever seen on his face. And as soon as I saw that smile, I knew I had been admitted to MIT, and I ran over to him, and we did what I like to call these man hugs, you know, how men hug each other. And so I was on my way to MIT. It was the most difficult and harsh thing I'd ever done. Many times I didn't think I could make it or did not belong there, but I did in the end. In 1973, I got my 2 degrees simultaneously in math and physics. And that was an accident, you see, because my grades were better in mathematics and I was trying to plan for graduate school, but I loved physics, so I kept taking the physics classes. My senior year, a friend of mine by the name of Ines Hope said, Jim, what degree are you going to get? I said, oh, I'm getting a bachelor's in mathematics. I'm a declared major. And she said, but we've seen you take all of those physics classes. What's that about? I said, well, I love physics. And so she took me over to the physics headquarters. They looked at my transcript. They said, you look just like a physics major, except in your senior year, you have to take the lab class and you have to write a thesis. And so I found I also could teach physics and mathematics, and that I love teaching and just being myself. And so although I got these 2 degrees, it was a total accident. And if it had not been for my friend Inez Hope, I would have come out as a math major. I am now in my 51st consecutive year of teaching, so I'm very grateful for those experiences. However, going to MIT was hard. And I like to show these 2 images so that people don't somehow think that it was just all laid out. I've often talked about my experience, and students say, oh, it was just sort of perfectly laid out to you. And I include this slide to remind myself to speak on the following. You see, there's an emoji here with a tear. That weeping represented my freshman year because I often cried about not being able to get the kind of grades that I wanted, not being able to do the homework without pulling all-nighters. Because you see, before I got to MIT, I never learned how to study because it wasn't necessary, even though I had ended up the valedictorian of my class. One of the things that I did learn while I was suffering all through my undergraduate time at MIT was I learned to bowl. And you might wonder, what in the world is that about? Well, you see, I always was a terrible test taker. And so when I would go to take a test, for the first 20 minutes, I would sit there and be unable to write or think anything. And then maybe about 20 minutes in, my mind would start working. And then I'd start writing. And then I'd write and I'd write. And by the end of the exam, I was writing as fast as I can. However, other students had 60 minutes to do that exam. I only had 40 minutes because of my emotional upset. So my tests were never very good. And oftentimes I would leave a test and then all of a sudden I would figure out even more answers. This created a tremendous amount of frustration. And so in order to work that frustration out, I learned to bowl. I like to tell students, you pick up a bowling ball at 16 pounds of dead weight, you have 90 feet of lane in front of you, and there are 10 pins at the other end. And sometimes you can imagine the faces of your teachers on those pins, and that might motivate you to bowl. By the time I graduated from MIT, the team I was on won the championship. That tells you 2 things. A, that I never got really good at tests, and B, I got a lot of practice because I wasn't good at tests. In fact, later I went to Caltech, and during those 2 years, we won the bowling championship there. And so I was essentially bowling at a professional bowling level because I learned that I had to do something to get rid of the intense pain for not being able to function at the level I thought I should in learning physics. These are some of my mentors. The lady up to the top left-hand corner is Shirley Jackson. She is currently the president of Rensselaer Polytechnic Institute, and she will step down after 20 years as its president. But she was my first physics teacher the summer before I started at MIT. The next lady you see is Vera Kistiakowsky. Vera's husband, George, is actually very famous. He was in charge of all the chemistry at the Manhattan Project in Los Alamos during the development of the atomic bomb. And she was also a physicist. And during my freshman year, she was my recitation instructor. And on my final, she did something amazing. I walked into her office because I had not done so well on the midterm. And I walked into her office in the final. And as soon as I walked in, she broke into an enormous smile and said, "Mr. Gates, you did it." I had gotten an A on the final exam. And what was encouraging was to see one of my professors, obviously not a person of the African diaspora, take great joy that I had mastered 801, which is the first physics class at MIT. And it was so encouraging that I've never forgotten that smile. And she, in some sense, got me used to the idea that I could have success at MIT, because every now and then I would do really well on a test. Margaret McVicker helped me in my graduate education. She taught me that I would never be an experimental physicist because her lab was a Kinesmatter lab. Udo Ingard was my advisor for my undergraduate thesis. And so I owe him a great debt. And then finally, James Young was my PhD thesis advisor. This is me in 1975, teaching calculus at MIT in the summer program, the same summer program where I had first met Dr. Jackson. And here I am about a year later. By this time, I'm taking teaching very seriously. The guy you see, well, I'm the guy with the goofy hat. But the guy you see pointing at me is a professor by the name of Brian Schwartz, who used to work at the National Magnet Lab. And Brian is the person who took me under their wing and started me thinking very seriously about how to be a good teacher. So by 77, I had earned my PhD, and my dad came to Boston to see the first member of our family to graduate with any degree at all. And he had never had a chance to go to college. And here I am graduating. So I work on a part of physics that's called elementary particle physics. We think about the smallest things in nature. And in particular, if you ask what those objects are, we can list them to you, and I've shown them here as a table. In the lower left-hand corner are the things that make up matter. The electron, you see this symbol E, stands for the electron, the mu particle, which is kind of an electron that's 200 times as heavy, and the tau particle, which is a copy of the electron that is 1,500 times heavy. There are the quarks that sit inside of protons and neutrons. You see them listed here. And then there are the particles that make up the force carriers. The photon is the carrier of the electromagnetic force. The Higgs boson is sitting up here. But you know, this is the universe that we know. But when I was in graduate school, I started working on an idea of supersymmetry, which says that there may be all of these other particles to discover in the future. And so I wrote MIT's first thesis on it in 1977. And you can see that thesis here. And then I went off to Harvard. But before I went there, well, here's the entrance gate to Harvard. But before I went to Harvard, I made a slight detour. I had a friend named Ronald McNair, and he and I had talked a lot when we were in graduate school. Some of you may recognize his name. He was the African-American astronaut who died in the Challenger explosion. And Ron and I both had been lovers of science fiction as children and had had many talks, and he had gone on to become an astronaut. So he challenged me to apply, and I did. And so as I was leaving Harvard and meeting people like this, Mark Grisseru, who was a professor at Brandeis University, who I'd later write a book with, Bruno Zumino, who was a professor, who was a theoretical physicist at CERN, and Peter van Nieuwenhuizen, who was the inventor of supergravity. I was studying works of these people by the time I was a graduate student, and that's how I got a chance to write MIT's first thesis on supersymmetry. In 1980, I met the gentleman that you see sitting down in the chair, Stephen Hawking. And so many times in my life, I was called upon to comment about Stephen's work, including on the occasion of his death for the BBC. But I went off to Caltech after Harvard. And at Caltech, I met these people: Murray Gell-Mann, a Nobel laureate in physics; John Schwartz, the inventor of superstring theory; and most of all, Richard Feynman, who was an amazing person. If you've ever read about his life, I tell people, if you read about Richard Feynman, all the stories are true. And so he had an enormous impact on me, although I never worked directly with him. This is me at Caltech, folks. Yes, the perfect spherical afro. And around that time, I started traveling abroad. In particular, there's a research center in Italy called the International Center for Theoretical Physics. The director was Abdus Salam. And Abdus had a large influence on my life because for 5 consecutive years, he made sure I had the opportunity to visit the International Center for Theoretical Physics. In the end, I decided the reason he wanted me to do that was for my own growth. He wanted me to see people from all over the world, from all nations, as they pursued physics at its highest levels. And in fact, on the occasion of my first meeting, he said something very interesting and mysterious to me. He said he thought that when a sufficient number of people of the African diaspora began to pursue theoretical physics, something like jazz would appear. I had no idea what he was talking about at the time, and I'll return to that later. So this is the book I wrote in 1984. As you can see, I'm one of 4 authors. Mark Grisseru, whose picture I showed you, Martin Wilczek, who was another young person like me, and Warren Siegel. We were like 3 kids and a very mature physicist, and we wrote the first comprehensive book on the mathematics of supersymmetry. But I've written other books in my life. This is the first book I wrote for the public. That previous book was only for people with PhD degrees in physics. This book was for the general public, but for the Italian public, L'arte della fisica. I wrote this book in the year 2000. because I was approached by an Italian publisher to write such a book. More recently, I've written a book called Reality in the Shadows, which is a book about the history of theoretical physics going back to about 2,000 years or so. And finally, I'm not sure what's going on with my software here, so I'm going to try to get back into the presentation. And then most recently, a book called Proving Einstein Right, which is about not Einstein, but it's about why his theory of general relativity was accepted. So really a story of a scientific band of brothers and the decades-long efforts they made to show that Einstein's predictions of gravity, which disagree with Newton's, were the ones that nature preferred. So the part of science that's mine, it's all mathematics, folks. I like to say I'm a fallen mathematician, because remember, my first undergraduate degree is in mathematics. And so it's something I dearly love, but I never thought I was a mathematician. I always was interested in the challenge of using extraordinarily complicated mathematics to describe our world. So because I talk to the public and people ask, what is a theoretical physicist? I'm going to share a story with you. A theoretical physicist is just like a novelist. You know, a novelist, and you know what they do. They use sentences and punctuations and paragraphs to tell stories about characters that they make up. Well, theoretical physicists do the same thing, except the characters that we write stories about are not ones that we make up. They're about elementary particles in my part, the electron, the proton, all those things that you hear about in science classes. Those are like characters to people like me. And we use mathematics to tell their stories. And so these equations that I'm showing you here are basically telling stories about that more balanced view. Remember, I showed you that we have the particles of the standard model, but if supersymmetry is correct, there will be more of them. The way we know about these things is because we understand the mathematics that tell their stories. And so that's what I learned to do in graduate school, to tell the stories, not just of the particles that we know, but about particles we might find in the future that you see flashing in and out on this display. But I don't just study equations. In order to do physics, remember I talked about imagination and my reading comic books, Marvel, science fiction, what have you, and Einstein's comment about the fact that imagination is more important than knowledge. Well, let me explain to you why his next sentence, because what he goes on to say is, what he says is, knowledge is about everything that we don't know now, and I'm paraphrasing slightly, but imagination encompasses the whole universe and all we will ever know. And that's exactly right. And so not only do I study mathematics, but I keep in mind that imagination is important. So by 2010, instead of looking at equations, I started thinking about some things that are kind of like crystals. And I and another scientist by the name of Michael Fox discovered these mathematical objects in 2005. By 2010, the British journal Physics World was asking us about these things. And so there's this article that we wrote explaining what these strange objects are. And they're our invention. Remember, I told you it's like being a novelist. Novelists get to make up characters, write stories. So Michael and I started writing the mathematical stories around these objects. These are some graphical representations of these objects. The thing that's really weird is you may say, well, gee, those are interesting and weird shapes, but these are also simultaneously the equations that I showed you earlier. And so we have this dual way of studying mathematics, both through pictures as well as through equations. Why pictures? Well, pictures because some large percentage of human capacity for reasoning is actually wrapped up in our ability to visualize and see. And so if you can see things literally with your eyes, you're tapping into a part of the brain that is much more powerful than what we normally have access to. So here's a picture of one of these objects, and unfortunately, the video doesn't seem to be working, but if I could get this video to work, you would see that there's a way to fold that object up into this. And the most odd thing about that folding is it involves error correcting codes. The same kind of error correcting codes that occur in computer science. And so this is the first piece of evidence that I'm aware of, that error correcting codes may be connected not to space and time, because there are a lot of people think that space-time isn't error-correcting codes. But what we found in our work prior to this upsurge in research on error-correcting codes was that those characters that we're writing stories about are connected to error-correcting codes if the world is supersymmetric, if it has that left-right balance. So error-correcting codes would be connected to electrons. I also do work looking at things like the cosmic microwave background. Maybe you have heard about it. It's the microwave signatures that are actually can be seen in the sky if you have a microwave detector, first discovered in '65 at Bell Labs by this device called the Homedale Horn. There's a sequence of satellites that were launched more recently to watch it. And here is the Planck satellite. And we can now see this object in the sky. And it looks like this, but you have to be able to see a microwave. You'll notice that they have pretty patterns, or some patterns. And so one of the things that I have done some research on is, could the idea of string theory be something that can mark these patterns? And again, you can see the use of imagination, because string theory is not normally thought about as possibly having an implication for cosmological structures, but if you know how to use the math, you can explore such questions. And so we wrote this paper on these strange patterns that are very much like the wheels on the moon that might be in the cosmic microwave background. Another aspect of my career is that I do science documentaries. These are things I never imagined when I was a graduate student. This is the first science documentary. It's called Breakthrough: The Changing Face of Science in America, and it was produced in 1995. And this is me in that documentary. I've done things like pilot riverboats, but not here in the US, but in Siberia. This is a picture of a riverboat called the Nikolai Maslenikov. And in 1996, I was in Siberia at a physics school, and I had a chance to pilot this boat. Hiking around the world. This is a picture from Venezuela on Mount Elavila. We've been on safaris. And I've included one picture of someone that you already know in this lecture series. Some of you may recognize this is Jocelyn Bell Burnell, who has been a previous Sowers lecture. And so I met Jocelyn on a safari in South Africa. Flown planes in Australia. And now we're in the part of my career that people don't normally think about being associated with an academician. I like to tell people, school is not in term during the semester. So what do you think we're doing? Well, we know what students do. They go on vacation. Why shouldn't a professor use that time to go on vacation? And typically we do. Now, it's true that we go to science conferences, and that's in fact what enables so much travel. But you often find yourself in interesting places like Brazil, where I had a chance to go down and a century-year-old gold mines that were worked by African slaves, or in Siberia to pilot a boat, or in Australia to fly planes. But another part of I found that my career has unlocked, as was mentioned in the introduction, is that I work in public policy. It's one of my careers. It's the youngest of my careers. Although I've been thinking about issues like college admissions for minorities since 1995, I've written some small series of essays. This is the first one. And this series of essays ended up in a very strange place. One of my essays was cited by the Supreme Court the last time the Supreme Court considered the question of whether diversity in admissions for universities was constitutional. Because of this, I think I am the only physicist living whose writings have been cited by the Supreme Court of the United States. I also have written popular essays on this. This is one that occurred around the time that Chief Justice Roberts asked a very interesting question. What unique perspective does a minority student bring to a physics class? And I responded to him with this essay. But I also have more directly been involved in public policy. This is a picture that was taken in 2009. As you can see, President Obama is standing there in the middle, and around him are the members of his Presidential Council of Advisors on Science and Technology. Standing next to him in a dark suit is his science advisor, John Holdren. And the rest of us were advisors to John and to the president. You can see me over in the corner. standing behind Shirley Jackson, who's in front of me. Yes, the same Shirley Jackson that taught me my first physics class at MIT in 1969. In 2009, I had joined her for this advisory group for President Obama. And over on the right-hand side, you can see a gentleman with silver long hair. That was Professor Ernest Moniz. He's a nuclear physicist at MIT. And I had known Ernie since I defended my PhD thesis because he was on my thesis defense committee. And remember how I told you how a word of encouragement from faculty means so very much to students? That's even true when you defend your thesis. So when I defended my thesis, at the end of it, Professor Moniz said it was the best PhD defense he had ever seen. And boy, did that send me soaring in terms of my confidence. We met in the White House with President Obama. The woman you see in the middle between President Obama and I was Valerie Jarrett. It turns out her great-grandfather was the first African-American to attend MIT in 1896. And yes, we had a chance to interact with the current president of the United States, President Biden. And I even got in trouble with my governor because I believe that politicians are supposed to obey the law. And in Maryland, the law says that the Maryland State Board of Education is the highest judicial body that decides on things that have to do with education. Well, my governor in 2016 decided to issue an executive order that overrode the school board. And he's never been challenged on it in court, but it resulted in my resignation because as I said, I don't believe that politicians or anyone should be allowed to break the law. So I resigned in protest. And to my great surprise, my resignation was actually a story in the Washington Post and the Baltimore Sun. So you can see part of it from the Washington Post here. My family had a chance to meet President Obama in 2013 on the occasion of my becoming a recipient of the National Medal of Science. And my two children, who you see here, apparently caught the science bug from their dad. This is a 2015 picture. My son is standing closest to me, and my daughter next to him, they're twins. And my wife is over on the left-hand side of this picture as I'm looking at it. My daughter has finished her PhD. She defended her thesis last spring at Harvard. She's now at Princeton, and she studies black holes as a postdoc. My son, I tell people, is a boy. And so he is still in graduate school, but it looks like he's progressing towards becoming a biophysicist. I tell young people, learn to use computers. This is my head obviously transplanted onto the Iron Man suit. My son did this for me because it's a joke, but learning to use computers is no joke, young people. So you need to learn how to use them. Why? Well, because it's the mathematical version of putting on the Iron Man suit. There's this problem in my part of physics that was first set up in 1979. It involves 4,294,967,296 unknowns. Now, what does that mean? Well, let's go back and think about algebra. You know, if I gave you a word problem, I might say, Mary and John both have $10 together, but Mary has $2 more than John. And then that's sort of the word problem that teaches you how to solve algebra problems. And of course, the solution is Mary has $6 and John has 4. Well, imagine a problem with 4 billion sets of unknowns. This was a problem that lies at the heart of quantum gravity and M theory. It's a problem that no one had solved since 1979. And part of the reason is simply the large numbers of degrees of freedom. If you're technically minded, you might recognize that thing in the white box. It's called a Taylor series expansion. And that's the thing that no one knew how to carry out, was this Taylor series expansion. And as I said, the problem started approximately in 1978, and no one knew how to solve it. And so in 2020, because my imagination is still very active, and I showed you that I had pulled the trick of learning how to think about equations in terms of pictures, we applied this idea, along with my PhD student Hazel Mott, and my other PhD student, Yangre Hugh, we applied this idea to quantum gravity and M theory, the kind of things that Ed Witten and John Schwartz and all those people do string theory, the kind of theory that they were talking about. Think of them as these kind of graphical pictures. And we were able to solve the problem. what we found is that the equations, first of all, that the equations had little boxes in them. Technically, these boxes are called Young tableaus. And if you take enough physics, you'll find out what those boxes are. But we could reimagine those equations as having a bunch of little boxes that had little Lego-like connections between them. And so we came up with this object using a set of rules that we gleaned from the equations, and this solved the problem of those 4 billion unknowns that no one had been able to solve in 40 years. And that's why Einstein's statement about imagination is so important, because it allows you to reimagine problems in ways that no one prior to you has done. And when you can do that, you can then solve problems. Another famous scientist is a computer scientist by the name of Alan Turing. And it is reputed that Turing said, sometimes it's the people, people who no one can imagine anything of, who do the things that no one can imagine. And folks, that's why diversity is important, because these habits of different thinking come with different people. And so that's my presentation. You've now seen what I do across a broad spectrum of activities, and I'm happy to take questions. And I hope I didn't put anybody to sleep. Thank you. Is anybody there?
Yeah, I'm here. Jim, thank you so much for your wonderful talk, inspiring as usual. I've heard some of the physics stuff that you mentioned, but and you told me a lot of stories from your life, but thank you for telling all the other interesting stories. It was really wonderful. We have a couple of questions. The first question I think that I received here was, I think, just after you mentioned your book in Italian.
Yes.
And the question was essentially, why did you choose to write a book in Italian? Well, why target that audience? If you could explain that to us.
Certainly, I can answer that, because you see, it's not that I chose, I was chosen.
You've chosen.
After I and my 4 colleagues, Martin Rovchek, Mark Grisru, and Warren Siegel, wrote our book for PhD physicists. That was in 1984. And so, you know, I never really had a yearning to write for the general public, because, George, you know me, I'm kind of a math maniac. I like to sometimes say, I love
definitely.
Deep and complicated mathematics makes me very happy. And so what happened in 2000 was a publisher. Remember, I told you I used to spend time in Italy at the International Center for Theoretical Physics. And,
in Trieste, yeah.
In Trieste. And because of that, I had about a 300-word Italian vocabulary in those days. It's all gone now, because I haven't had a reason to use it. But I had some familiarity with the language. And there was a publisher called De Renzo in Roma, who had become aware of me and thought I was an interesting character. And so he asked me to write a book, L'arte della fisica, the art of physics. And so it wasn't that I chose, I was chosen. And I'm crazy enough to take a challenge or dare. And so I thought writing a book for the public in another country was like, who would expect something like that to happen in your life? And so I went right ahead and plunged ahead and completed the book.
Oh, wonderful. There is a question that I actually received in chat. It's a little bit along, very serious question. What makes MIT and Harvard different from other universities? And what advice do you have for VT STEM major students to overcome differences they encounter?
Sure.
And also, yeah.
Okay, I can see the chat. So let me take this question.
Yeah.
Because Harvard and MIT are not like each other. They're very different from each other, at least at the undergraduate level. I tell people I'm an MIT product. I was an undergrad at MIT. I was a graduate student at MIT. I was a postdoctoral research fellow at Harvard. And so the main thing about undergraduate MIT versus undergraduate Harvard is that undergraduate MIT is dedicated to STEM. You don't get through MIT unless you have a fairly sophisticated and high level of engagement and understanding of mathematics. That is not true of Harvard. You can not have that level of understanding and be successful at Harvard. So that's a big difference. When you get to the postgraduate level, or maybe the graduate level, the two of them, together with places like Caltech, Stanford, University of Chicago, Yale, and all of the Ivy League, yes, at that level of graduate education and postgraduate education, they are very similar. So what's different about them? Well, first of all, they all have far more resources than most universities to dedicate to things like crazy ideas like supersymmetry. I mean, when I was there at Harvard, there was no idea that this weird combination of math and physics might be something that you could go to the laboratory and test and try to observe. That happened much later after I got my PhD. And so because they have the funds to support such, well, in the language of Silicon Valley, you would say that these are blue sky explorations. They're not things that are going to affect your bottom line right now, but they might uncover some hugely important ideas for the future. And so these universities have the funds. They have, just like Dr. Sowers supports the lecture here, these universities have many, many alums who will support their efforts to look at not just the things that are practical, but the things that are impractical, but that might be extraordinarily important for the future. And for people who don't understand this, let me just tell a story. In the 1850s, there was this young person by the name of James Clerk Maxwell, and he wrote down these 4 equations. And supposedly at some point, he had a laboratory, and at some point, a minister for the Queen came to his laboratory, and he showed them spark chambers. I don't know how many of you are horror movie fans, but there's this famous movie called Frankenstein, where the mad scientist has this room with lights and electricity. It's sort of like that. And so the minister came and saw all that stuff, and he, at the end of his visit, he said, well, all that's very interesting, but of what benefit is it? And supposedly the answer was, I don't know what the benefit is, but I'm sure that people like you will tax it at some point in the future. And that's exactly right. This is the beginning of telecommunication, electrification, radio, television. All that comes from these 4 equations. And so we, in the history of Western development of science, we know what some of these crazy blue sky ideas can turn into, because in fact, the very fact that we're able to talk to each other goes back to those 4 equations. And so that's why universities that have lots of resources are able to fund this sort of thing. And then the second part of the question is, what kind of advice do I have for Virginia Tech STEM majors, students, to overcome these differences, or those differences? Well,
Yes.
obviously I was different. I was so MIT normally admits about 1,000 students in each academic year. And the year that I came to MIT, 50 of those students were African American, so clearly we're in a vast minority and we're very unusual. And so what advice can I give to, see, the difference that this question is about are not really differences that are exclusive to ethnicity. They're not differences that are exclusive to gender. They're not differences from the multitude of identities that humans can have. The most important things I found were pretty few, actually. A, you have to have a rock hard faith that you can do it. No one can give this to you. It can be taken from you by experiences, but no one can give this to you. This is something that has to be core to who you are. And in my case, as I have explained to people, for whatever crazy reason, I was convinced that the universe had a problem out there that had my name on it. That is a problem that only I could solve. And now at age 70, I've actually solved such a problem. This 4 billion unknown thing that was around for 40 years and no one could solve. I solved it along with my graduate students. And I have to thank all of my researchers for the contributions they made to this journey. And so that's one thing I would tell your students, is that you have to believe in yourself and have hope that the universe is such that there's a way for you to be successful. The second most important thing I know is to be yourself. Not to try to be someone else, but just to be yourself. And then the next thing is that it is very likely that someone will be happy to be your mentor. That person doesn't have to look like you. They don't have to have the same gender. They don't have to have the same ethnicity. They don't have to have, like I said, various other ways of identifying yourself. But those people are likely there. And I found them in my MIT experience. So those are things that I think that are most important. And then the final part is be willing to take a lot of pain, a lot of crying, a lot of tears, and work really, 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 really hard to make yourself the most excellent version of who you have the potential to become.
Thank you, Jim. That was very inspiring. There is a second part of this question, but I think I want to move to some Q&A questions. There is a question about what are your thoughts on Emmy Noether's work? I think your commentary on diversity is exemplified by her, and I would love to hear about your reflections. Obviously, very famous person. Maybe you should say a couple words for the general public
Sure.
about Emmy Noether.
Hang on a second. So first of all, Emmy Noether was someone that most non-physicists have never heard of. But even Einstein admired her work.
Yeah.
Most people have heard of conservation of energy or conservation of momentum. Well, Emmy Noether is the person who established the most deep mathematics about why things are conserved. And so it's Emmy Noether that we in physics owe a great debt to for teaching us this great principle about conservation of energy, conservation of charge. All of these things fit into her mathematics. And for that, Einstein was an enormous admirer for her. I'm sorry, George, I see a question in the chat.
There is a second one in Q&A. Do you have any advice on how to become a successful physicist in today's day and age?
I suspect, well, first of all, as I alluded to with that cartoon with my head on the Iron Man suit, learn to use computers. Because even if you're not trying to do something that winds up in the design of a device or characterizing an experiment, learning to use coding and computers is the mathematical equivalent of putting on eyeglasses. You know, we wear eyeglasses to see better. Learning to use computers, your mind can engage mathematics at a far deeper level than without them. So that's one very key thing, is invest in yourself by becoming familiar with computers. And I have to tell you that I was lucky that summer that in 1969 that I was at MIT, I learned Fortran.
Yeah,
and
me too.
I learned to use the code, those stupid cards with holes in them. And I had the occasional dropping those cards, and therefore all of my computer program was right out the window. Learn to use computers. They're amazing. And they're not, to my mind, the proper way to use computers is that they become adjuncts of your mind, additions to your mind. They're not separate things. They're things that become part of you. And you need to become extraordinarily comfortable with their use, because that's where, when you harness your imagination, which so far, that's the one thing we can't see in computers. We don't see evidence of imagination. If you harness your imagination to the ability to compute, you can do fantastic things that no one has ever done before. And that's what we did with that 4.2 billion unknown problem.
What is the proudest accomplishment of your career, in your opinion? Is this?
In my scientific career, it's this recent work that we solved this 40-year-long unsolved problem. I have lots of other things that I'm proud about. For example, in 2006, I wrote an article in which I said that the LHC would not discover supersymmetry. And it didn't. This article is actually in Physics Today. I can point it out to anyone. And furthermore, in 2014, I said, I still didn't expect it. to discover supersymmetry, and it hasn't. So in theoretical physics and particle physics, as you well know, George, most people thought discovering supersymmetry would be extraordinarily easy. I thought it would be extraordinarily hard. And I said so publicly at a time when essentially nobody else was willing to say it, based on my understanding of how nature works. And so, remember I told you the universe has problems with my mating one? That's one of them, apparently.
On the president's committee, when you work with President Obama, did string theory ever come up? If so, how?
Not really, not directly in any way. I was once asked to talk about my research in string theory, and so I did, because other members of the advisory group were not theoretical physicists. They were spread all over the STEM domain, and so people really want to know. They want to have someone just give a set of explanations, and so yeah, that's the only time string theory ever came up, was when they asked me to explain what I do.
Okay. So there is a question about that. Do you think, I don't know, they say that even though we are not, I guess this is referring to Virginia Tech, a prestigious school like MIT or Harvard, we can still become great and respected physicists like yourself. I'm sure you have the positive answer to that.
Well, I do, George, because if you look at the arc of my story, I went to a high school where we had to share desks because there were not enough desks for the African-American students in my classroom, so I had to share desks. Our books were falling apart, but the thing that made the difference was that A, we had teachers that were invested in our success, and B, we understood the magnitude of what we were competing against to be successful, and were willing, much as athletes, every athlete I know who achieves greatness has an intrinsic understanding that you don't do that without putting your whole being into it. And so it's that willingness to totally give yourself over to an endeavor that I think makes a crucial difference. And that's a matter of what's inside of you. And so, yeah, I think this student from Virginia Tech, particularly since I know you, George, and Laura, and Eric Sharp, who are scientists that I respect, I know that you can train these students to be successful at places like MIT, Harvard, Caltech. So the names don't matter so much. And in fact, in physics, as you can probably explain to students, George, in physics, it turns out that the quality of a physics education is incredibly flat. Namely, that something like the top 50 or 60 schools that have graduate programs of physics are just epsilon different from each other, certainly in theory. And so,
I agree. Yeah.
And so that's not an issue for us that it might be for some other people. George,
Well,
I'm sorry, there's just one comment that I feel I have to address. It comes from Mr. Jiang, I think is the way to pronounce the name. The question is, as a Black person, how did you get into MIT after enduring so many obstacles, stereotypes, and discrimination? And how did you continue your studies at MIT, a predominantly white institution, and what difficulties did you face? Virginia Tech's College of Engineering and College of Science are also predominantly white institutions. What advice do you have for Black students? Well, a couple of things. I have done enough science. So let me tell you, I told this one story earlier today, George. I'm going to repeat it. I was in Switzerland when I was very young, but after my PhD, and I gave a talk. And as usual, when you give physics talks, people come up afterwards if they have questions, because nothing's ever completely clear. And so I started answering the questions until finally there was one person left out of the crowd. And he came up and he said, I don't really have a question. And he made a statement to me, which was, I have never heard a Black man speak the white man's magic so well. And, I recognized that implicit in that statement was that he didn't think that I should be able to, that I should be able to do this. And so the first thing that I tell not just a Black person, but any person who's a minority of whatever axis, is that the first thing that you have to do, as I have said earlier, you actually have to believe that there's something inside of you that no one else can do. And you have to believe that fervently and completely, because it's that belief that will get you through the tough times. The next thing is that you have to look for people who are going to help you. You have to be open to have mentors who don't necessarily share your gender, who don't share your ethnicity, but who share in a belief that intellect and knowledge are important and that you have a gift that you can develop along those lines. Or as Dirac once said, to be satisfied to make even a small contribution to the great effort. That's a paraphrase, but Dirac made that statement. I think those are the most important things to do. To seek out those people who are going to help you, no matter what their ethnicity is or gender or whatever. And that's what got me through, and not just me, there are other, I know there are not a lot of Black physicists in the world, but all of us who have gotten through have found this pathway to join with other people like you, George, George is probably ashamed of this, but George is a dear friend of mine. I've known George for what, 40 years now, George?
34.
30, 40, something like that.
Yeah.
And so as a minority person, you can't assume that every person in the majority hates you, because not everyone does.
Thanks, Jim. There are some questions about the nervous high school student, nervous about the upcoming AP physics exam. Any advice?
Oh boy, well, not really. I would say some people take these classes to get higher scores on the standardized test. Those are basically a waste of money as far as I can tell. They may teach you some few strategies and what have you. Only thing I know is learn the stuff as well as you can, try to relax on the day that you take the exam, and hope that the universe is with you. That's the only thing I can say.
There's another, there's a light question here. What is your Marvel Comic Universe superpower?
What is my Marvel comic universe superpower? No one's ever asked me that question before, George. I would say that it's the way that I combine my imagination with mathematics so that I can sort of see crystals in the form of equations and vice versa. That's probably the closest thing I have to a superpower.
So what is something, some subject you're not an expert in, but find extremely interesting and exciting to learn about? I think you were telling me biology recently, right?
Biology, yeah, my son is majoring basically in biophysics, and I find that extraordinarily interesting at a deep intellectual level. However, to me, the most interesting subject is actually history, because if you know enough history, a lot of things that seem mysterious about the world actually can be understood. So for example, our country is undergoing a terrible challenge to democracy. I have a sister several years younger than me, and if you could speak to her, she would tell you I've been saying this time was coming for the last 20 years, because it's completely obvious, if you know the cycles of history of our nation, that we would have such a time. I don't know what the outcome is going to be, but it was completely obvious that we were going to head into this time when the very idea of democracy might not stand, because that's where we are as a nation. And so learn history, because it lets you have a broader view of human behavior that, in my life at least, has also allowed me to be successful as a physicist, because I kind of understand the history of physicists. There's this beautiful book called The Physicist by an author named Kevles, I think the first name.
Yeah, yes.
And if you read that book, you'll learn about the history of the physics community in the United States.
Yes.
I read the history very young in my life, and it gave me some insights that I would commend to any young physicist, even though the book itself is quite old. But that history is actually very important.
It's a classic. Regarding the importance of diversity in math and physics and the fact that imaginative solutions can come from unexpected individuals, do you have any specific examples of students who surprised you with particularly creative solutions to solving problems?
I have had such experiences. They don't happen super often, but they happen regularly enough that one comes to understand that the one secret of solving problems is being able to look at the problem without assuming that there's no answer. Because students who have this knack of providing unusual solutions, they typically come at the problem from an angle that nobody else has thought about. And so it's the ability to get outside of the box, so to speak, that is the secret to innovation. And that's what I try to bring to my work. And when students surprise me with solutions, it always seems to have that element of getting outside of the standard box.
This question is about your teaching, which is very important for you. Obviously, you said 51 years and going. When you first started teaching, were there any particular experiences you drew from to help inform your teaching style? It's clear that you greatly respected your early teachers, so I'm curious whether there were any techniques you borrowed from them.
So my teaching, as I showed you folks a picture of me in a goofy hat and a professor by the name of Brian Schwartz pointing at me, I am kind of a product of Brian's ideas about teaching. He took me under his wing and told me how he taught and what he thought about students. And I started to emulate him. One thing, the first lesson he gave me was, when you're teaching, the first thing you should do is tell the students what you're going to teach them. The next thing is that you teach them. And the third thing is that you tell them what you taught them. And that if you go through this complete cycle, then you're shortchanging the students. And that's that may seem like a joke, but it's actually very, very real if you get in the classroom, that you have to go through those steps. And so, that's the first thing I learned from Brian. He also talked about technical things like learn how not to, when you give a lecture, don't face the blackboard throughout the entire lecture. Now, this may seem obvious, but lots of professors seem to forget this lesson. And then the other thing is, as you're teaching, try to watch the eyes of your students, because they're going to guide you about whether you're losing folks or whether they're getting it. And in particular, it's very strange, and George, you can speak to yourself, but when students get there's an idea that they catch on, there's literally almost a light that goes on in their eyes.
Yeah, I agree.
It's a very strange thing. But if you're teaching a classroom, you've experienced this, and you know that this happens when students catch on to something. And so Brian told me to watch out for those lights.
So there are two questions that are sort of, I think, related. One is, what was the most exciting moment for you in your career? And of all of your published works, which one was your favorite to work on?
Well, I've actually answered my favorite. It's my latest ability to, this ability to turn equations into crystal means that we effectively have the mathematical equivalence of MRIs. That is, we can look at inside of equations with the specificity and fidelity that no one else in the world currently has. And so that right now is my current favorite. I have past current favorites, like when I finally figured out how to write down four-dimensional string theories with no reference to higher dimensions. I was extraordinarily happy about that outcome. And there's a sequence of things that I think of as the highlights of my career, where I've done things that are different from anyone else and that had not been done before. And so, but right now, it's the 4 billion problem.
Yeah. With all advancements we made in the past 100 years, what do you think are the most exciting areas of research in physics physics currently?
They're at the boundaries, in my opinion. And by boundaries, I mean physics and. So physics and biology, physics and economics. There's this thing called econophysics out there. Physics and data information. People talk about data science, but physics is a data science. I mean, the sorts of things that people talk about data science are, for people like you and me, George, they're sort of like bread and butter of how you do great theoretical physics. And so physics and data science, physics and computers. It's the physics and places I find most exciting these days.
Right. So this is a question about your work during Obama years. What policy were you able to affect while working for President Obama? Do you
Oh,
feel
that's
like you had an impact in the political sphere? Some general comment?
Well, yeah, the answer is yes, and I'm very, as you can see, I'm smiling. So let me tell you just a couple of stories there. So maybe some of the young people on remember something called Schoolhouse Rock, which was a cartoon that used to come on Saturdays. And there's this one particular story about how a bill becomes the law. And there's this bill that marches up the Capitol and blah, 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 blah. And so I've actually lived that life. There are things that I wrote about in reports to President Obama that later became parts of US law with impacting education. So those were big favorites of mine. Every time that the Obama administration looked at issues around education, I was one of the lead authors. So I was very happy to lead those efforts. But my favorite story of those years was an effort where I wasn't a lead author, but I was part of the writing committee. In 2012, we were in a meeting and the president said that people from the FCC had come to him with a problem, namely that people were buying Wi-Fi enabled devices at such a rate, smartphones, what have you, that if it continued, we would not be able to allow everyone to have access because you would have interference. So the president said, I want you to find a solution to this problem. And we actually did. It turned out it was relatively simple. Namely, the interference that goes on with radios doesn't actually happen in the air, because in the air, Maxwell's equations hold. And as you well know, George, Maxwell's equations allow for the principal superposition, which translates to, in the air, signals travel right through each other, and they are totally unaffected. The interference actually occurs at the receivers and possibly at the broadcast devices. And so where you have to fix the problem is there. And what we did is looked at a range of technologies, including the way that the internet works. I don't know how many people know how the internet works, but it's based on a technology called message packaging. And it turns out that if you just convert radio receivers and transmission devices so that they implement the digital coding of message packaging, our studies showed that you could increase the capacity for the spectrum by at least a factor of 10,000. And so we made this report to Obama and his White House. They started implementing some changes to allow this to happen, because whenever you talk about spectrum, it has to go to the Federal Communications Commission and one other agency in government. And when we made our report, it was really funny because the major telecommunications company said, oh, that's just a group of ivory tower professors. They don't know what they're talking about. Mm-hmm. But eventually they figured out that we did all our calculations right. And they moreover figured out that if you increase access by a factor of 10,000, that means more customers. And so that directly impacts the bottom line of their businesses. So within about 4 or 5 years, they became the biggest. They went from a position of those crazy professors don't know they were talking about to this is the greatest thing since apple pie. So that was a funny thing to watch, how our reports actually impacted the country. And almost no one knows about this particular report, but I can point you to it if anyone's interested. And it allows so many people now to have smartphones.
Fascinating, fascinating. We have actually quite a few other questions here. I don't know how we're doing with time, but let's try to press it. How did the discovery of the Higgs boson at CERN affect your work at that time?
It didn't affect my work at all, because I'm looking out at the physics well beyond the Higgs boson. So it had no impact on me, except that it was on my bucket list of things in physics I wanted to see in my life.
Very good.
That went off.
Dr. Gates, what advice would you have for those who seem to be stuck in classicist understanding of education? Quote unquote, hey, I'm not at X top school, therefore I won't achieve anything, end of quote sort of mindset.
Well, first of all, I don't give advice, because in my mind, advice assumes you know far more about the person that you're giving it to than you probably do. All I can tell you is that when I was in that segregated high school in Orlando, Florida, which you know, and many people say, you know, there's no chance in the world you're going to get a chance, you're going to have the opportunity to work on problems that would have stymied Einstein. I didn't listen. I could imagine myself doing such things. And that's where the power of the imagination is so powerful. And so imagine that you can do these things that you want to do. And imagine it sincerely. Imagine it deeply and with all your heart. That's, for me, was the secret.
As a second-year physics student, I enjoy learning about the major very much, but I'm unclear on what my career path will be. Do you have any advice or guidance for specializing in a particular area of physics and working towards a career?
Well, again, I don't give advice, but I can only tell you what I implemented. I've often said to people that, especially young people, when they ask me such a question, I say, you know, I asked that question at one time in my life. And what I decided was that I would do what I love most, because it seemed pretty clear to me that if you love something, you'll work at it really, really hard. In fact, it won't seem like work. And if you're of even moderate intelligence and you do it a lot, you're likely to get really good at it. And if you get really good at it, other people won't notice. And so that's the thing that I found worked was, first I have to ask, what is closest to my heart in this, all the things that I'm studying? And for me, it was elementary particle physics and gravity.
Right. There are two related questions. Have you ever experienced burnout in your career?
Of course.
And have there been times when you doubted your ability to become a successful physicist?
Of course, of course. Let me go back. During my senior year at MIT, I told you about my freshman year when I was really just emotionally a wreck. During my senior year, it happened again. And I came very close to having a nervous breakdown. But I recognized what was going on. I pulled myself back from it. So yeah, I used to get, well, Winston Churchill is famous and was the Prime Minister of England during the Second World War. But he also suffered from severe bouts of depression. He called it the black dog.
Yes.
I know the black dog. And so one of the things that I think is most important is that when and if you meet the black dog, it's important to figure out what emotionally do you need not to let the dog take you down. Because that's what I did whenever I met the black dog. I told you about one strategy, learning to bowl. There were a couple of other things that I did, but I won't share with you because they're terrible advice to give a student, but they worked for me. So each person should have some idea of their psyche, of their mentality, of their personality. And maybe you can find some unconventional things that will provide you with the emotional relief that you need to escape the clutches of the black dog.
Winston painted, as you know.
I do know, as one of his ways to get away from the black dog.
Right. Okay, I think we should probably try to wrap it up because now I see Mark Pitt coming up.
Yes.
Sorry, I cannot answer all these questions, but we've been going for, I think, 35 minutes or definitely 30 minutes. So I'm going to thank you, Jim, and once again for this wonderful talk. And I'm going to sign off and leave Mark to sort of conclude the talk, the event. Thank you very much, Jim. We'll stay in touch about physics and everything else. Bye-bye.
Thanks, George. So I'm Mark Pitt. I'm chair of the physics department, which is the host department for tonight's event. So Jim, if you don't mind indulging one more question, I saw one on here that I thought may be a nice one to wrap up with, if that's fine, if I can ask that. And
Go ahead, sure.
So this is from Samantha. I think I know who Samantha is. She says she's somebody who's interacted with you in the past. Is someone who has had the opportunity to interact with you first as a high school student at a Smithsonian lecture, and then as a college student when you were presenting at PhysCon 2016, which, as you know, is an event that reaches lots of physics undergraduates. And now as a teacher, she's a teacher now.
Oh.
You've had a cumulative effect on my education and career trajectory. She's a teacher in high school physics. And what she's asking is, I'm now interested in education policy, especially STEM education. Do you have any advice for me on any connections I should make or any programs I should look into in that area?
So Well, I've talked about my policy experiences. They're not something that I set out to do. They started very small. When I look at my policy career, it actually starts when I was still an assistant professor at MIT. I was asked to design a physics curriculum for the Boston School Committee, and I did it. And so for me, I mean, the secret was start small, gain experience from that meager experience of writing a school curriculum. I started talking to teachers, and I had occasion in my mid-career to begin to speak to groups of teachers at conferences and to sort of understand the problems that many of them wrestled with. And so I did it essentially by accretion. I kept getting experience and experience. And then finally someone asked me to do something like go on the state school board. And so I had always taken the opportunity to speak at high schools whenever I was invited. I would speak to educators more generally whenever the occasion came up. And I started reading some policy literature about education. What is it that educators are debating? And so those are the steps that I found. I don't know if they'll work with Samantha, but that's what happened to me.
Great. I'm sure she'll appreciate that advice. So with that, I really, Professor Gates, I really want to thank you again on behalf of tonight's big audience we had here, the colleagues you met with in the university here earlier today. And we want to thank you for the wonderful lecture and this, 40 minutes now you spent answering questions. You did allude to this earlier. I see from your online CV that you've visited us here in Blacksburg. If you don't remember the years, it was 1985 was the first time, 2003 was another time. Maybe there were other times I missed in there. We're really sorry we couldn't visit you here in person, but we really appreciate this opportunity to interact with you. So with that, I want to thank you again on behalf of everybody here. And we're looking forward to seeing you tomorrow in a physics department colloquium. So
Okay.
Thanks again. And you and everybody else have a great evening.
Sure. Thank you, Mark. And everyone, I hope you do have a great evening. And for the young people out there, believe in yourself. That's the most important thing.
Wonderful message. Thanks, Jim.
Yep.